Okay, we are going to take a look at cell stoichiometry. So, similar to other stoichiometric relationships, we need a mole ratio. So we need that from either our half reactions or a net reaction, depending on what we're solving for. And in our redox reactions, we can solve using our mole ratios to calculate mass, time, current, and or charge. So, charge is determined from the electrical current, which is I. Oops. So it's I. This guy here is current. And time. And Q, if you remember from our previous lesson, is charge. So if we look at the example that I have below, it says the technology of the Hall-Héroult cell for producing aluminum has improved considerably since the first industrial factory. Modern electrolytic cells may use up to 300 kiloamps of current. What is the charge that passes through one of these cells in a 24-hour period? Now you might notice that we have a few things that we need to do before we solve this. So first we have our units in kiloamps and we have it in hours. So we definitely need to start with some unit conversions here at the beginning. So the first thing that we can do is our time conversion. So we can convert our 24 hours and we can multiply that by a fraction that equals 1. And in 1 hour, that equals 3,600 seconds. Which means that in seconds, if I plug that into a calculator, that equals 8.6, sorry. Let's erase that. So 8.6 times 10, oops, different color, that's okay, times 10 to the 4 seconds. Okay, so that's my first little conversion there. And the second is I need to have my kiloamps in amps. So I have 300 kiloamps. And that equals, okay, that's going to equal times 10 to the 3, or if we have if you prefer your scale, and I use Kermit has dandruff but doesn't care much. If I have 300 kiloamps, the decimal's here. I'm moving it 1, 2, 3 places over to the right. So 1, 2, 3 places over to the right, which is 300 times 10 to the 3, or 300,000 amps. All right, so if I'm looking for the charge in coulombs, so if I'm looking for Q, all right, I know that Q is equal to 300,000 times by my 8.6 times 10 to the 4 seconds. So this is amps and this is seconds. And when I plug that into my calculator, I get 2.6 times 10 to the power of 10 coulombs. All right, now what you might notice here is this is a very large number. This is a huge amount of charge being transferred, and this is in this aluminum cell. Now, if you compare that to a light bulb, a 100-watt light bulb in 24 hours would be about 7.2. So a light bulb is 7.2 times 10 to the 4 coulombs in a 24-hour period. So that is way more charge here. This is a huge amount of charge being transferred through the cell. The important thing to note is Q equals IT. Okay, so now we look at this thing called Faraday's law. Faraday's law is a combination of our charge and Faraday's constant. So Faraday's constant, he made this constant as 9.65 times 10 to the 4 coulombs per mole of electrons. Now, in an equation, we have the number of electrons. So this guy equals the number of electrons. Okay, again, I is current, and that will be in amps. T is time in seconds, and Faraday's constant. Okay, so this is number of electrons equals IT over F. So we can do a variety of things to calculate this. The first example that I have here is what amount of electrons, so number of electrons, or moles of electrons, is transferred in a cell that operates for 1.25 hours at a current of 0.15 amps. So this equals IT over F. So I'm looking at my current is in amps, so I have 0.150 amps times by my time in seconds. Now remember that if I have 1.25 hours in 1 hour, that's 3,600 seconds. So I'm going to multiply these two numbers together, and when I do that, I get, let me just plug that into my calculator, I get 4.5 times 10 to the 3 seconds. So I'm going to put that in here, 4.5 times 10 to the 3 seconds. That is a 3, although it doesn't look like one. Okay, so I'm then going to divide that by Faraday's constant, which is 9.65 times 10 to the power of 4, or exponent of 4, and that's coulombs per moles of electrons. Now, our amps is going to cancel out our time. Okay, it's also going to cancel out our coulombs. So seconds and coulombs will cancel out, giving us moles of electrons as our resulting unit. So when I plug all those values into my calculator, I get an answer of 6.99 times 10 to the negative 3 moles of electrons. Okay, so you can see how this is a relatively simple calculation. A few things that you need to keep track of is your time units and your units on your amps, just to make sure that when you plug these in, that you have the right units. The units on your Faraday's constant should never change. It should always be coulombs per mole. Now, generally, people, when they plug this into their equations, they don't write this unit down because in order to figure out what you cancel out, you have to know that 1 amp is a coulomb per second. So 1 amp is equal to a coulomb per second, and that is why we can cancel out our coulombs here as we can cancel out our seconds here, and giving us moles of electrons as our answer. So, as you can imagine, since this is stoichiometry, we probably need to talk about some kind of mole ratio. We haven't talked about a mole ratio yet, and we need to take a look at that. So, let's take a look at a few more examples, just simple plugging numbers in with Faraday's law, solving for different variables, and then we're going to take a look at that mole ratio. So if we convert a current of 1.74 amps for 10 minutes to amount of electrons. So again, we're calculating number of electrons equals IT over F, which means that we have 1.74 times 10 minutes, and again, 10 minutes is 10 times 60, which means that 10 times 60 is 600 seconds. So we have 600 seconds over Faraday's constant, which gives us an answer of 0.0108 moles of electrons. All right. Another quick calculation here. It says how long in minutes, so if I'm calculating for time, will it take a current of 3.5 amps to transfer 1 mole of electrons? So if I have NE equals IT over F, okay, and I'm looking to solve for my time, okay, I can rearrange this. I'm assuming if you are in Chemistry 30 that we are pretty good at rearranging formulas as of this point. So I have number of electrons times my Faraday's constant, okay, and that is going to be all divided by current is equal to time. So if I plug this in, I have my number of electrons, or my moles of electrons, which is 0.1 moles, times my Faraday's constant, divided by my current, should give me 2.76 times 10 to the 3 seconds. Now again, because this is asking for in minutes, which is an important thing to note, I need to change this unit here of seconds into minutes. So in 1 minute, there is 60 seconds. So I'm going to divide this value by 60, and I get that this equals 46.0 minutes when I plug that into my calculator. Okay, so these are the basic calculations that we can do with Faraday's law. Now let's take a look at these half-cell calculations where we will be looking at mole ratios. So the mass of an element produced at an electrode depends on the number of electrons transferred. Now this can either be mass produced or mass lost. So that means that we need a half reaction with number of electrons, okay, or moles of electrons transferred that's needed for this from this stoichiometric calculation. Okay, so we need it from our equations for this calculation. So let's just jump right into some examples here. It says, what mass of copper is deposited at the cathode of a copper electrorefining cell operated at 12 amps for 40 minutes? So again, the first step I'm going to do is I'm going to say my number of electrons equals IT over F. Now this formula is something that you will need to know going into a diploma. Be very familiar with it. They will not give it to you in your data booklet. Okay, Faraday's constant is given in your data booklet, but this equation is not. So we have IT over F. Now, again, we want to write down any of our variables. I like to sometimes just jot them down. So I is equal to 12 amps. T, time, what's going on here? Time is 40 minutes, which if I multiply how many seconds are in a minute, I would get times by 60 seconds. So that means that I have 40 times 60 seconds is 2400 seconds, okay, in 40 minutes. And Faraday's constant, which is 9.65 times 10 to the power of 4 coulombs per mole of electrons. So that's my first step. I can calculate my number of electrons. Another thing I might want to consider is that my half reaction is copper 2, because I'm dealing with copper deposited, copper is going to be my product, okay, plus 2 electrons, 2 moles of electrons gives us copper solid. So what we're looking for here, and with every other stoichiometric calculation that we've looked at so far, we use our reaction as an organizing tool. So I'm looking for my mass of this. In order to calculate that, I need my moles, which I can get from a mole ratio, and my molar mass. Okay, then I can use my mole ratio from my number of electrons, okay, which goes here from this overall formula. So my first step is to calculate my number of electrons, which is going to be equal to 12 amps times my time, which is 2400 seconds, divided by my Faraday's constant. So when I plug that into a calculator, I get that this equals, so my number of electrons is equal to 0.298 moles. Okay, now this is moles of electrons. Just like any other stoichiometric calculation, I need to look at this mole ratio. So my mole ratio, according to my half reaction, is 1 to 2. I have 1 mole of copper solid, okay, to 2 moles of electrons. So if I take this number, divide it by 2, that gives me 0.149 moles of copper solid. So now that I have my number of moles of copper solid, I can plug that value in for here, 0.149 moles of copper solid. Again, I can use my data booklet to get my molar mass of copper. So if I just jump over to, let's see, my data booklet. All right. I can go and find my number of, my molar mass of copper, which is 63.55. So I'm just going to pull up a new color here. So 63.55 grams per mole. Oops. So when I go to calculate my mass, which I'm just going to do at the bottom here, my mass is equal to my moles times my molar mass. This formula you should be very familiar with as of now. Okay, and my moles is equal to 0.149 times my mass of 63.55, or my molar mass, pardon me, grams per mole. This will give me an answer of 9.48 grams. So if this runs for 40 minutes at 12 amps, I'm going to get 9.48 grams of copper. All right, there gives you a bit of an idea of how this works. Again, number of electrons is moles of electrons, and we get that mole ratio from our half reactions here. Now this half reaction, if you didn't know it right away, it is off your chemistry data booklet. Again, if you were to scroll to page 7 here, we see that our half reactions are here, and for copper, it's this guy right here. So again, if you are unsure of that half reaction, it's simply off your data booklet. Now, these half cell calculations can be done for both voltaic and electrolytic cells. Okay, it can be used in both types of cells. Let's continue to look at a few examples here. So this example says silver is deposited in objects in silver electroplating. Now, electroplating is an electrolysis type cell. So it says if 0.175 grams of silver is deposited from a silver cyanide solution in a time of 10 minutes, predict the current. So this time we're looking to calculate current. Again, I can use my half reaction. My half reaction is silver ions from our silver cyanide solution, and 1 electron is transferred to make a silver solid solution. Or silver solid solution. I meant to say silver solid. Okay, so I have write down my variables. I have my mass, which is equal to 0.175 grams. And my molar mass of silver, let's just slide this guy over and find our molar mass of silver. Okay, our molar mass of silver is 107.87. grams per mole. All right, and we can calculate moles here. Now, I also know that with my electrons here, I need my electrons for current. Current is all about my electrons and the movement of those electrons. So my formula, if I rearrange my Ne equals IT over F to calculate for my current, I'm going to have number of electrons. My current is going to equal my number of electrons times by Faraday's constant divided by my time. So again, I have my number of electrons. This will be from my mole ratio. Faraday's constant I have some time, given is 10 minutes. So I can write these variables down. 10 minutes. My number of electrons is going to be mole ratio value. Faraday's constant, 9.65 times 10 to the 4. And I'm calculating for my current. So let's simply start plugging these values in. For this first calculation, my number of my moles from my mole calculation is mass over molar mass. When I do this calculation, my mass is 0.175 grams divided by 107.87 grams per mole. And that initial calculation gives me 1.62 times 10 to the negative 3 moles. And this is moles of solid silver. if I do a mole ratio here, okay, I have my solid silver on the bottom because I need to cancel that unit out. I have my electrons on the top. In this case, it is a 1-to-1 mole ratio, which means that this equals 1.62 times 10 to the negative 3 moles of electrons. So I can plug that number into this, 1.62 times 10 to the negative 3 moles. So when I do my calculation that I have to do in purple, which I'm actually just going to sneak up in this right-hand corner here because I'm running out of some space, I have my current equals my number of electrons times Faraday's constant it's 9.65 times 10 to the 4 over my time. Again, my time is 10 minutes. Now, remember, we need our time in seconds. So I have 10 minutes times 60 seconds, which is 600 seconds. So when I do that, I get a current. If I plug that into my calculator, I get a current of 0.261 amps. Okay, remember amps is coulombs per second, okay, because current is the flow of charge, okay, so and a rate of charge flow. So we have 0.261 amps of current. Now, when we're, again, if you needed a procedure for this half-cell stoichiometry, we always want to start with a balanced half-cell reaction. So we always start with this guy here, our half-cell reaction. Okay, we can convert our measurements that we need to. So we have time in seconds, mass in grams, moles, and amps. And we want to convert those measurements into amount of moles by using that appropriate conversion factor, whether it be a concentration, whether it be a molar mass or Faraday's constant, whatever it might be to convert that number of moles. Okay, once we do that, we use a mole ratio to calculate the amount of the required substance. Again, whether we're looking for the solid or the mass of that entity or in reverse to calculate current, we're going to use that mole ratio. And then again, we're going to follow that up with the other calculation required. In this case, we used our Faraday's law equation as our second calculation. However, that can be the first calculation, again, depending on what you're calculating for. So remember, you always go from your known to your moles to moles using your mole ratio, and then to your what you're looking for, or your unknown. So your known to your unknown using this magic mole ratio. All right. Now, at this point, stoichiometric calculations should be quite familiar with you because we've done quite a few in Chemistry 20. So this is just an extension of that, except we're using a new formula. So just like we've done gas and solutions in gravimetric stoichiometry, this time we're just doing what we call as cell stoichiometry. So we can look at those number of electrons that are being moved in these half reactions. So at this point, if you need to go back and take a look at some other examples, you can do so now. And I would suggest definitely taking some time, pausing the lesson to make sure you're really following through with the steps and you have them written down appropriately in your notes. Okay, good luck.